detection rate depends on the properties of dark matter, which is what we'd like to see, what we'd like to learn about, and also the probability for the interaction with the nucleus, since that's what we build our detector on. Okay, so you might have seen plots like this before. These are exclusion plots from direct searches for dark matter. So here on the horizontal axis, we have the mass of a dark matter particle. Here on the vertical axis is the interaction cross-section for some weakly interacting massive particle with a proton or neutron. Right? These lines here come from different experiments, and above the lines, all of this parameter space is ruled out. So for example here, if the WIMP mass is 10 to the 2 GeV, and the interaction cross-section is 10 to the minus 47, this parameter space, dark matter could still live there, it's not ruled out by experiments. This is how to read these plots. Future experiments push down further and further into this region, searching for dark matter interactions. So one thing to note here is that these plots are always made with this axis. This is the WIMP nucleon, that's the weakly interacting massive particle with a proton or neutron cross-section. But what's really measured in the detector, or not measured, is the interaction of a dark matter particle with a nucleus. Typically a very large nucleus, something like xenon, with 130, 140 protons or neutrons. And so what's happened is an implicit translation between what's ruled out, which is the interaction of dark matter with xenon, and what you'd like to know, which puts constraints on your theory model space, the interaction of dark matter with a single proton or neutron. So how do we do this? So essentially, what's usually used is the Born approximation, and that is that we have a nucleus, and if we have dark matter interacting with the nucleus, we're going to assume that it interacts with just a single proton or neutron. So this single interaction with a proton or neutron, this is something that we can calculate from lattice QCD, for example, the numerical method that I was describing, for a number of different types of dark matter particles. You can calculate how does that interact with a single proton or neutron. You can multiply it up by the number of protons and neutrons and say, okay, that's your dark matter interaction with the nucleus. Calculate the scalar matrix elements, and we calculated them for different nuclei. So for deuteron, proton-proton, helium-3, and these are different combinations of quark flavor depending on how the dark matter couples to the different quarks inside the nucleus. And what we see is 10% deviation from 0 here is our naive expectations, our Born approximation, and this is as a percentage. So we see 10% deviations from the naive expectation. So 10% doesn't sound like a lot, but this is 10% in a 3-body nucleus, helium-3. And then you want to multiply that up to 130 or 140 body nucleus with controlled uncertainties. To give you an idea of the magnitude of this, there's a famous problem in nuclear physics known as the quenching of the axial charge. So axial matrix elements, just a different type of matrix element to these. These are what are called scalar matrix elements. There's another type, axial matrix elements. In helium-3, the axial matrix elements have 0.01% deviation of what you'd expect by multiplying up. In a nucleus with 40, 50 bodies, they have 20% deviation. And we're seeing for the scalar matrix elements, already 10% in 3-body. Right? So what this is really saying is that these are unexpectedly large nuclear physics effects, multi-body effects in the scalar interaction, which is precisely what's relevant for interpreting dark matter direct detection experiments. So you can't neglect this in the interpretation of dark matter direct detection experiments. Essentially, there are very large uncertainties on these the exclusion plots that we've seen. Okay, so what about larger nuclei? I said that this was in a 3-body system, and really dark matter experiments are done on, for example, xenon, that's a 130-body system. How do we get there? So the program really is to use what's called nuclear effective theory. Essentially, we do know that 1-body interaction should be dominant, 2-body interaction smaller, 3-body interaction smaller still. We have an expansion in the interactions. So the idea is to determine 1-body contributions from calculations, 2-body contributions from 2-body calculations, 3-body contributions from 3-body calculations, and plug them into an expansion to as many orders as we can go, and then use that expansion to get to larger nuclei. And so we match the effective theory and nuclear many-body methods like the examples I showed before, where the predictions for, in that case, the double beta decay major element were varied. We try to match those expansions, ground them in the standard model by fixing the free parameters, not by trying to match to experiments, but fixing the free parameters to the standard model. Ultimately, however, it would be really interesting to be able to go further using direct numerical methods. So there's just a host of these what are called intensity frontier experiments that I explained at the front of the talk that use nuclear targets. Everything from, so the DUNE, this is the Deep Underground Neutrino experiment. It's the multi-billion-dollar experiment, next generation experiment in the United States looking to measure neutrino masses and their mixing parameters. This uses neutrino scattering on an argon target that's A equals 40. Double beta decay rates, the lightest nucleus that can undergo double beta decay is calcium, that's A equals 48, that's larger again. The largest dark matter experiment is xenon, that's A equals 131. So these are the sorts of nuclei that we really want to understand. And again, understanding how finely tuned the emergence of nuclear physics, the periodic table is in nature. Again, we need to go to larger nuclei. As I said, these are exponentially harder problems. And so if we want to do this directly, we need exponentially better algorithms. So over the last 18 months, last couple of years, my group's been using machine learning as an ancillary tool to try to accelerate lattice QCD calculations. So the applications of machine learning in this area are really particularly interesting because we have to be very, very careful. We want to preserve the fact that the formulation we have is a rigorous approach to studying a quantum field theory. We don't want to insert a black box at any point of the calculation where an error on the machine learning side means that you get the wrong physics out. So you have to preserve a rigorous approach to a quantum field theory in all of the right limits. And ultimately, we're looking to accelerate all parts of the workflow of these sorts of calculations, or from generating the snapshots of the background quark and gluon fields through to extracting physics from those snapshots, if we need to be exponentially accelerated to reach any of these large nuclei. So I'll give you just one example at the close of the talk of a way that we can use the same machine learning technology that's used in image recognition problems in something like Google image search for these sorts of calculations. So neural networks are, of course, what's used for image recognition, and they really excel on problems where you have something where the basic units of data don't have a lot of meaning on their own, but in combination you have something meaningful. So that's like an image. You have pixels, which are not meaningful on their own. You have an image, and you can train a neural network to tell you that this is gliding blood and not something different. Right? This is a prototypical example of an application of machine learning. So I won't go into the details, but there's a problem within these lattice field theory calculations that we can frame in exactly the same way. So we can accelerate our calculations if you can train something to take an ensemble of configurations, which are snapshots of the background quark and gluon fields, described by a bunch of real numbers, not integers, real numbers, right? If you can train something to take that ensemble of configurations and tell you the parameters of the action that's basically the standard model parameters that correspond to those configurations, then we have a way of accelerating our computation significantly. So phrased in this way, you can see how you might be able to train a neural network to answer this problem. The problem is that this is still, even on the scale of machine learning problems, extremely challenging. So here's a benchmark image set used for machine learning. So images, right? You have some number of pixels, 32 by 32 with 3 colors. So something like 3,000 numbers describing an image. You can, of course, train on larger images, but this is a fairly standard set. And you have 60,000 samples. And this is what a lot of image recognition codes are tested on, right? This image set, of course, each image has some meaning. It's a cat, or it's a dog, or it's a shoe, right? Local structures are important. Within a picture of a person, you have structures like eyes and a nose that are meaningful on their own. And you have some translation invariance within a frame. So a face over here in the frame is also a face, even if it's in a different place in the frame. This is sort of the structure of image data sets. On our hand, an ensemble of these gauge field configurations is something like 10 to the 9 numbers per sample, compared to 3,000 numbers for an image sample. And we have maybe 1,000 samples that our calculations are done on, as opposed to, say, 60,000 samples for this benchmark image learning set. So we have what's called an inverted data hierarchy here. We have far more degrees of freedom per sample than number of samples, which makes it a real challenge to train, even from a machine learning perspective. There are other differences, so it's really a collection of these samples that has some meaning. We're trying to do an average over all possible paths, and it's really only the average that's physics. It's long-distance correlations that describe the physics. As we said at the start, I talked about correlation functions over some distance telling you the mass of a particle. It's really those long correlations that are important, not local features. We also have a lot of interesting symmetries, things like gauge symmetries that come into these problems. So ultimately, this is a challenge from a physics perspective and from a machine learning perspective. But we were recently able to show that you can take lattice gauge fields, you can train some custom network structure that respects the complicated symmetries of the problem, emphasizes physics at the right physical scale to get the few parameters that you want out the other side, and thereby accelerate these numerical calculations. So this is really nice. It's complete. It uses all of the information encoded in the fields. It has some training costs, but once it's trained, it's also very fast. And so we can use in various ways machine learning as a tool to augment our simulation. So here's just an example that shows that this works. Here's a case where there are two parameters of interest, one related to the lattice spacing. Remember, we put physics on a finite grid, and there's some spacing of the grid points. And here's a parameter related to the mass of the quarks. The dot points here, the stars, are the parameter values used for training, and the ellipses show the predictions from the neural network. The direction of the ellipses and the direction of constant physics, this all makes sense. You can make predictions at closely spaced intermediate values. And the particularly nice feature about this is that if the prediction is wrong, if you're aiming for this ellipse and you actually get a point up here, it actually doesn't change the physics of your calculation, it just makes it slower. So essentially, if you have a well-trained neural network, you have a big speed up. If you have a badly trained neural network, you still get the right physics, it just doesn't accelerate your calculation. So it's a safe way of using machine learning for these calculations. So we're at the stage of proofs of principle of these sorts of approaches. And the hope is that this will help us accelerate and eventually reach calculations of larger nuclei. Okay, so finally, of course, the other question is, what about new computational paradigms? So this is such a computationally limited problem. And again, we're investigating potential future uses of quantum computing to apply to this task. I have a student just graduating from their master's who has written an algorithm that uses quantum computing. If future quantum computers will come to exist in a useful way for us, that would be able to use quantum computing to accelerate these calculations. And then something I'm really excited about is the possible use of custom hardware for a single calculation. So the idea of field programmable gate arrays, these are FPGAs. This is an old idea. We have a computer chip that's essentially reconfigurable as an end user to some extent. These have in recent years become much better and much cheaper, which gives us now a potential way of customizing a network of these tailored to a specific calculation in a way that we couldn't before, up to even networking the entire thing into the same four-dimensional structure as the calculations, and reconfiguring the chips to the precise calculation that has to be done. This could also offer several orders of magnitude acceleration on these calculations. So these are really the future directions for getting to a large nuclei. Okay, so in summary, the title of this lecture was Nuclear Physics from the Standard Model. And so we're really at the point where nuclei can be studied from the Standard Model, and we're really in the early days of this. The current state of the art still has significant systematics, but there have still been phenomenologically interesting results, right? We can say that multi-body interactions are important for dark matter direct detection experiments, and before constraining models of dark matter, we have to understand them better. We can start to understand double beta decays, for example. And so in the near future, or really this year, we've started running the calculations that will control these systematics for light nuclei at least, for helium-3, helium-4. We're on the edge of the first controlled calculations. And so really understanding these nuclear matrix elements is important to experimental programs and new physics searches sort of across nuclear and particle physics. Everything from understanding the flaw and structure of hadrons and nuclei to future electron-ion collider, understanding neutrino physics, understanding dark matter, and just understanding how the complexities of the periodic table come from that wonderfully elegant standard model. Thank you.
Thanks for the excellent talk. Questions? Some questions. When you talk about the machine learning, okay, so
Yes.
you want to speed up the calculation. What type of factor you are talking about? 10, 100, or even more?
Yeah, so what I showed is really a proof of principle. So in that case, it was more of something like a factor of 10, but that's a very dependent question because that actually depends on how many samples you need because there's an upfront cost. So then if you need more samples, that cost is sort of amortized over the number of samples you need. So it depends on the problem, how much that's worth it. For a problem where you need few samples, it might not be worth it at all. For a problem where you need very many samples, it can be a very significant speed up of many orders of magnitude. So that's a problem-dependent answer, and also this was a smaller scale than state-of-the-art calculation. So we've not yet scaled this to a state-of-the-art calculation.
Well, another question is about your tremendous probability.
Yeah.
Yeah, this way. So we're talking about the 2, 3 neutron that they can do 3
So what we're really looking at is this is a well-defined matrix element. The dineutron is not bound in nature, right? But in our calculations, we can make it bound. And this matrix element is the well-defined sub-process of the double beta decay of a larger nucleus. So it's not really 2 free neutrons. It's that sub-process of the beta decay of a larger bound nucleus.
Yeah, but then when you see, for example, last diagram, you connect the 2 neutrinos together.
Yeah.
Then you have some loop, some momentum dependencies.
That's right. You have to integrate over the neutrino energy.
So that's taking care of it.
Yeah. So in the published work, it was for neutrino full beta decay, but one of our postdocs, David Murphy, has done this for the neutrino-less case, and so those results are almost out. They'll be out this year.
So how far away this is to real application? Because say in your bottom measure sort of calculation, let's say multi-nuclear sort of similar change significantly.
Yeah. Yeah. So this is sort of slightly different because in the dark matter case, what changes significantly is when you look at the actual you're looking at the 2-body interaction and the 3-body interaction and the 4-body interaction. That's what changes significantly. Here, we're always interested in the 2-body interaction. The question is how many spectator nucleons you have. So that's a different scaling of the effects. So ultimately, this is not in calcium, which is the largest nucleus that undergoes double beta decay. But you expect the spectator nucleons to have far less effect than they do, for example, in the dark matter case. Because again, they're not involved in the interaction. Because even in calcium, it's a 2-body interaction that happens with the double beta decay.
More questions?
Thank you. So I have a question about the double beta decay.
Yeah.
I'm a condensed matter person, so this may be a very naive question, but so are there any constraints on when the 2 neutrinos annihilate? What are there is it possible they're not just annihilating and that being it, but also emitting either energy or some other type of dark matter particle that we don't know about? Because then of course the problem is you wouldn't see that, like the energy of the other 2 beta particles wouldn't necessarily be a very clear signal. It would still be less than the whole energy of the decay.
Yeah, so you want...
I don't know if this is a good question. So
you want a model of dark matter which has a vertex with 2 neutrinos in a dark matter particle.
Yes, I have no idea if that's a reasonable thing to ask.
I don't know of a model like that.
Yeah, I can make a comment on that. When So this here is a neutrino has a neutrino Majorana mass. And then if you have this that number is divided by spontaneous system equation, then you will have a Majorana. So the Majorana might connect to two neutrinos. So when you connect it, you have a Majorana come out. That's come out to be sort of invisible. So that's probably one of the example closest to your case. And then that has been studied parallel also. And then now with the calcium theory, there's really neutrino-less probability without a Majorana. This is a case of a Majorana.
More questions? Yes.
I have a question on the machine learning on the
Yes.
data QCD example.
Yes.
Suppose I have an example of the NF2 plus 1 plus 1 and then example. And then with the known parameters. Then the machine learning tell me what are the proper parameters for doing the simulation for 1 plus 1 plus 1.
Yeah, so we haven't tried it for anything past 3.7. So, and also when I was a bit vague, what we're really using is using that as part of a multi-scale algorithm. So we're not really asking what are the parameters to do the simulation at. We're asking, so if you want to go to a coarser grid, yeah, so if you want to go to a coarser grid and do hybrid Monte Carlo on the coarse space, which is more efficient, what are the matching parameters to go from the coarse scale to the fine, which is the reason we're asking the question of what are the parameters of the action to start with, because
So your question is say just changing this other scale, okay, and then what would be the parameter?
it's basically trying to do the normalization.
Not changing the number of variables.
That's right. That's right. It's trying to do the normalization group flow.
But can it be done anyway?
Can you change the number of
Yeah.
labels?
Can the machine learning help?
Yeah, that's a different problem. I don't think you'd use a neural network. But one of these Bayesian optimization tools might work. But you need a lot of different parameters with different Quark masses, which would be expensive, right? And a lot of different simulations to explore the space.
Yeah.
Good. More questions? Yes.
There are several groups in the world who are doing this lattice QCD calculation on radio. For example, the Bonn group by Meissner, the UK group by Oxford, and the Service group, the CIO, and this JF group, etc. So can you give a quick summary on the difference in the directions that they pursue of these several groups?
Yeah, so okay, so you say the Savage group, Martin's one of my collaborators there. And the people who became the CalLAT group were also former collaborators. And so the approaches are very similar, looking at slightly different physics problems. The only major difference is with the HAL QCD group, who are doing a completely different approach based on potentials. Whereas so we're doing an approach based on constructing the nuclei via contractions and so on, and they're doing a potential-based method. And all of the groups in the United States are doing the same as us in terms of approach. Yeah, so the Japanese group are doing the potential-based stuff, and what was the other group? They're not doing nuclei. So Meissner's doing many body models on the lattice, not lattice QCD. So he's doing essentially nuclear many body models, also on a discrete space-time, but they're not based on the standard model. They're based on nuclear models.
More questions? Okay, if not, then thank Professor Shanahan again for this very nice talk.